right, it is a great pleasure to introduce Ryota Mikami from Tokyo, who is going to tell us about the the tropical analog of the Hodge conjecture. Ryota.
Thank you so much for introduction, and I thank the organizers for this opportunity to talk. So, our long goal is to study the cycle class map. Sorry. Sorry, so it seems. Sorry, okay. So, cycle class map. It's classical object, but there are several important problems, such as Hodge conjectures. So we propose a tropical approach to these conjectures and problems. So tropical geometry is a combinatorial shadow of algebraic geometry and enable us to deal algebraic subvarieties. To combinatorial objects. So, and tropical geometry have many applications to problems of algebraic subvarieties, such as Gromov-Witte invariant. And we want to use tropical geometry to study cycle class map. In this talk, we focus on the Hodge conjecture. So let us remind the Hodge conjecture. Let X smooth projective variety over C. Then the image of cycle class map is contained in the Hodge class. I mean, the intersection of PP cohomology and rational cohomology. Okay, and the Hodge conjecture states that this map is surjective. So to study this map, we consider tropical cohomology. There is a tropical cycle class map defined by Liu from Char groups. So our strategy is first, today, we show that this used tropical cycle class map is isomorphism. And in the future, we want to study a map between tropical cohomology and to the Hodge classes. Okay, so this is our long goal, and today More precisely, we prove the next theorem. Let X smooth algebraic variety over field K, for example C, and we fix, also we grip is okay with the trivial variation. This is a kind of non-archimedean variations defined as follows. The image of 0 is infinity, otherwise 0. Okay. Then is tropical cycle class map. It's isomorphism. So this is the main theorem of today. And as a corollary, the Hodge conjecture, the original Hodge conjecture has corollary, the Grothendieck standard conjecture D, which states that homological equivalence is numerical equivalence. And as a corollary of tropical analog of the Hodge conjecture, we have analog of Grothendieck standard conjecture. We assume X is projective, then the kernel of cycle class map to tropical homology. This is a dual of tropical homology. So since tropical homology is dual of tropical homology, the kernel of this map is just algebra cycles numerically equivalent to 0. Okay. So let me give more precise main theorem. In fact, we show that for any H and P and Q, tropical homology is isomorphic to the specific homology of the sheaf of tropical K groups. I mean, the sheaf of tropical analog of K groups, of Milnor K groups. Okay. The first main theorem follows from this main theorem. So we will define tropical analog Milnor K groups later, but let me give more. So we will define tropical analog of Milnor K groups by using tropical geometry, but there's other more easy definitions. So then K is characteristic 0, and for extension field, tropical K groups is isomorphic to, we consider rational coefficient always. Subgroup of K differential of L over K generated by dfi over fi wedge dot wedge dfp over fp for fi in L non-zero element. Okay. And so the shape of tropical analog Milnor K group satisfies the the shape of tropical analog of Milnor K group satisfies the Kelvin resolutions. The next, this resolution. So here xi is the codimension I point, and kx is the residue field at x, and ix is a natural map. The first term we consider sum of a generic point and the KTP of kx, and the next is the sum of codimension 1 point and the KTP minus 1 kx, and we consider the residue map, and so on. In particular, the P's term is KT0 is isomorphic to Q, KT1. There's the natural surjection from Kx times to KT1 Kx, and there's a natural. And this map is compatible with taking divisors. So this implies, so HP X star KTP is isomorphic to Char group tensor Q. So main theorem 2 implies main theorem, the first main theorem. Okay. So today we prove this main theorem. And before we prove main theorem, let me remarks related to works. So remarks. So there's other tropical approaches to the Hodge conjecture. So for some Algebraic varieties, in 2009, there was an announcement by Professor Katsarkov and Kontsevich. And recently, there's Tarkov's paper on Kontsevich's idea. which is idea. Yes. Okay. So there's announcement and on papers on ideas, but it seems as far as I know, there are no results still yet. Okay, so to study our main theorem, so our strategy is so for higher dimensional algebraic varieties, to study its tropical gestion is in general difficult. So to avoid difficulty, we use the theorem on general cohomology theory. And to apply this cohomology theory, also sorry, this is not my theorem. This is first proved for algebraic theory by Quillen and developed by many mathematicians. And to apply this theorem to tropical cohomology, we need to prove M homotopy invariance. Then, so our main theorem is follows from this theorem. Okay. So in this talk, first I'd like to define tropicalizations and tropical cohomology and tropical K-groups, and then prove main theorem. Okay. So first define many things. In this talk, let K be a field with the trivial variation. Let me define tropicalizations. So let this sigma a toric variety corresponding to a fan sigma. Let GMN a dense orbit spec Km M. We consider subvariety across subvariety X. So we expel the Berkovits identification, which is a set of variation of height 1, which is trivial on K. I mean, VAB equal VA plus VB, V0 equal infinity, V1 equal 0, VA plus B is greater than or equal to minimum VA, VB. Yes. So for each sigma, we put trop the map from the orbit, Berkovich identification of the orbit to homomorphism from M cap orthogonal to M2R defined by V to its restriction to M cap sigma orthogonal. Then, so the image of X pair is called topicalization, is the finite union of cones, rational polyhedral cones of dimension equal dimension X. Okay, this is the basics of tropical geometry. Here, cones means the closure of cones in the usual sense. Okay, next let me define tropical cohomology. So for simplicity, let me assume X proper. I mean, trop X is compact. Okay, so let lambda a fan structure of trop X. So let me remark, right? Cones in this talk are closure of usual cones in for each P we put FPP or FPP trop X is the wedge product of M tensor Q cap orthogonal to sigma P, where sigma P is the cone in sigma such that interior of P is contained in tropicalizations of the orbit corresponding to sigma P. Okay, here P is the closure of usual cone, so cones. Okay, so modulo F, sorry, the restriction of F is equivalent to 0 if the restriction of F to the wedge product of spans of Q is 0. Here Q runs through cones in lambda and P contain Q and sigma P equals sigma Q. Okay, I mean Q is the Q and P is the same of it, and P contains Q. Okay, P, and we put for each P and Q CPQ trop X lambda to be sum of P of dimension Q FPP tensor HQ P delta P Q. Okay, the latter is isomorphic to Q, non-canonical. for this CPP, there's a natural boundary map from CPQ drop to CPQ plus 1 drop. I mean, for each F lambda, F, these two F. Okay, as usual. And we put tropical cohomology as a cohomology of this map. And for given x, we put tropical cohomology of x the limit consider families of morphism to toric varieties. Its tropicalizations and tropical cohomology of tropicalizations. And we consider pullback and toric morphism. Okay. Taking limit, we define tropical cohomology of x. So let me give an example. So when x is defined by x plus y plus 1 in P2, then so top P2 consists of 7 orbits. The dense orbit is R2, and there's 3 orbits of R. And there's 3 orbits of dimension 0. And trop x is in this case this set, and this consists of this half line, 3 lines. So in this case, tropical cohomology of trop x, when p equals 0, this is isomorphic to usual singular cohomology, which is 0 or q. When I equal 1, I equal 0. Okay. And so the interesting part is H11. Let me compute this. So this is C11 modulo image of C10. C11 consists of, so there's 3 one-dimensional lines, L1, L2, L3. So C11 is 3-dimensional. Consists of, so dual of each. Sorry. Dual of each span Li, and for it, so this direction is x, let this direction y. Then for C10 it consists of qx plus, it's just qx plus qy. And this image is obviously so two-dimensional. And this is isomorphic to Q. And in fact, X is isomorphic to P1, and L1 corresponds to exadic variation of X. Variation to L1, and y-adic variation corresponds to L2. The infinity and the infinity corresponds to L3. And this map corresponds under this identification. This map corresponds to taking divisors of X and Y. Okay, this is so. This example. From this example, it seems that tropical cohomology looks like Char groups. Okay. So next, let me introduce tropical K groups. Remind that Milnor K groups, let L over field over K. Then the Milnor K groups, here we consider tensor Q. It's a wet product of L times tensor Q modulo L minus J. Okay, this is the Milnor K groups. And we put tropical K groups L over K, or for simplicity, we sometimes write KTPL is the limit of FP0 of phi spec L closure. Here phi runs through morphism from spec L to GMN over K. And the limit is taken for toric morphism. The commutative diagram, there's a morphism and the toricalizations, and there's a pullback map is well defined. Okay. This is tropical K groups, definition of tropical K groups. And so let me copy. As I said in introduction, there's another expressions. Okay. I mean, this FP, so we fix a function structure of we put the closure of phi spec L Wi-Fi for simplicity. For function structure, lambda of top Y phi. Consider its closure in the toric variety. T lambda corresponding to a lambda. Then, so codimension of Y phi, closure of Y phi, cap or P in Y phi per here P in lambda is dimension P. This is because topicalizations of algebraic variety is the dimension of algebraic variety, and topicalization map is proper. I mean, okay, so moreover, we assume Y phi bar minus Y phi is a simple normal crossing divisor, and Y phi is smooth. Then, in this case, and we assume K equals C in characteristic 0, then Fp0 is isomorphic to image of wedge product M tensor Q to so image of residue map to residue of df1 f each wedge dfp fp. So by these observations and definition of topicalization, we use non-archimedean geometry set of variations. We can consider FP is just this set. And by using mixed Hodge theory, this is isomorphic to image to, for example, P, so Wi-Fi. Image FP to df each over 1 df1 to dfp over fp, for example. Okay, and this gives the expression of tropical K groups I explained in introduction. Okay, just taking limit. Okay, and so next slide. So this tropical K group satisfies good properties like Milnor K groups. Here we omit the proof. In the sense of lost, I mean cycle module of lost. This is a this is a framework of objects which behaves like Milnor K groups, and in particular, so again, let me explain again. Particular, there is a Gelten resolution for its simplification on smooth algebraic variety X. Here, Xi is the codimension I point of ski, and Kx is a residue field at X, and Ix is a natural map. And we consider tropical K group as the Zariski on spec Kx. So each term is codimension I point of X and tropical K groups of P minus I. And the maps are the residue map of tropical K groups, which come from the residue map of Milnor K groups. Okay. And so I explained once. So again, the P term KT0 is isomorphic to Q, and KT1 from Kx times to KT1, there is a natural surjective map. And this map compatible with taking divisor X. And hence HP X Zari KTP is isomorphic to Char groups tensor Q. Okay, so we've defined everything. So let me remind the main theorem. For X smooth algebraic variety over a field K with a trivial operation, then its tropical cohomology is isomorphic to Zariski cohomology of tropical K groups. This implies a tropical analog of the Hodge conjecture. Okay, so next, I'd like to give a proof of this main theorem too. So okay, let me use the next slide. Proof of main theorem 2. Okay, first we assume proportion. One, the excision. I mean, one morphism, phi, and the closed subscheme of the target, such that fine bus D is isomorphic to Z, then HPQ trop. The relative cohomology HPQ trop ZX is isomorphic to the relative cohomology fine bus Z X prime. And A1 homotopy invariance. I mean, there is a natural isomorphism from X times A1. The tropical cohomology of X times A1 and that of X. Okay. So here first we assume this proportion, and we will prove A1 homotopy invariance later. And since ether excision is easy, we omit the proof. And sorry. And the proof of A1 homotopy invariance is the main part of the proof. Okay. And this assumption, by this proportion and plus more when K is finite. We can apply a theorem on general cohomology theory. To tropical cohomology. I mean, this theorem is just the existence of Gersten resolution. This is first proved by Quillen for algebraic K groups. And then generalized by Bloch-Ogas and generalized by Gabor. And we use the framework of Coryotterner, Hubler, Kahn. And note that lost cycle module is a kind of this theorem. Okay, more precisely, we consider conic spectral sequence, that is the E1 PQ term is for sum of codimension P point X, consider H, oh sorry, we fix R here, and P plus Q trop XX, which converges to tropical cohomology of X. Here this trop XX means that limit of open neighborhood U of X and HRP plus Q trop relative cohomology of X bar in U. Okay, this conic spectral sequence so whose its term is by the theorem of general cohomology theory, whose its term is the recessive cohomology of the signification of tropical K group, tropical cohomology. Okay, so then by definition, its PQ is 0 for K is smaller than -1, because this becomes 0 in this case. And also E1 PQ is 0 for Q is greater than or equal to 1. This is because when we put AX, the set of variations contained in Berkovich analytic space, such that the morphism from the variation ring to X under this map, the image of maximal ideal is X. Okay. Notice, so when V is X, then rank of V, I mean rank of the image of V is smaller than or equal to codimension of X equal P. So sorry. This means that H, sorry. So the even term is, roughly speaking, is the sum of HP plus QX, certain shift cohomology on this closure of this X and relative to X. And this is 0 because for Q is greater than or equal to, sorry, I missed. This is R greater than or equal to. For Q greater than or equal to 1, this set is, since for each V, the rank of V is smaller than or equal to P, X is just a dimension smaller than or equal to P. And so this set is 0. And for each P plus Q minus 1, X bar minus X FR. So, sorry, I have only a small space. This set has a two retroaction to the set of the closure of AY. Here, Y is the generalizations of X. And hence, so this set is a union of dimensions smaller than or equal to P minus 1 set. Hence, for Q greater than or equal to 1, this set is 0. Hence, by long exact sequence, this HX, P plus QX, XX bar, AX bar this is 0. Hence, U1 PQ is 0. Okay, so and we also have AR0 trop is isomorphic to tropical K groups. This is because when P equals 0, X is a point, easy to calculate. When P equals 1, X is a line. And on this line, the FP, the coefficient FP is constant on this line. So we can compute, in this case, easily. And we can show that this HR0 trop is isomorphic to sheaf of tropical K groups. Okay, consequently, its term is 0 when Q is not equal to 0. So its P0 is isomorphic to infinity P0, that is tropical cohomology of X. And its P0 is Zariski sheaf cohomology of tropical K groups. Okay, this is the main theorem too. Okay, so far we see that when we assume these propositions by using a theorem on general cohomology theory, we can easily show that our main theorem. So the key part of the proof is to show A1 homotopy invariance. Let me give short explanation. So if the pi is another projections, then so we know that tropical cohomology is just shift cohomology on Berkovich analytification of some shift. Okay, so we use ray spectral sequence. So we need to compute this higher direct image of Fe. So I mean, sorry. So we computed the stocks. We fix V0 in X pair and topicalization of X times A1 pair. Then what we need to compute is a certain cohomology on trop pi inverse V0. Yes, this computes the higher direct image at Stokes. Okay, so under suitable interpretation, what we need to compute is certain residue map along the topicalizations. Okay, let me explain this. What is it? First of all, let me identify pi inverse V0 and its topicalizations. Under some assumption, we can identify topicalization and a subset called tropical skeleton. And this set pi inverse V0 is isomorphic to Berkovich analytic space over a variation field. Okay, V0, which is the completion of K support V0 by V0. So, okay. This is non-archimedean variation field. And we consider adic space. Adic space is a set of variation of any height and which contains the Berkovich analytic space. And for each V in this lattice, so near V, so there's a point. There's a point near V of height 2 variation, which is contained in adic space but not contained in Berkovich analytic space. This W is a specialization of V. And for each W defines a discrete variation on the residue field of V. Residue field. So we need to compute what is this map. And to compute this map, let me note that the residue field of V is isomorphic to K prime S. Here S is indeterminate. And K prime is a finite extension of the residue field of V. So in this case, so the set of W, which is corresponding to the variations on the residue field of V, which is trivial on kappa V0. Okay, so since the residue field of V is isomorphic to K prime S, so this is isomorphic to the closed point of P1 K prime. And the next short exact sequence enable us to compute the residue map. The first term is tropical K groups of KT. The second term is tropical K groups of K prime S. The last term is the sum for closed point of A1 over K prime. And the map is residue map. Okay. This is an analog for that of Milnor K groups. Sorry, let me give one more minute. So by this long short exact sequence, we can compute this residue map along this graph, which is a topicalization pi inverse V0. And by induction, we can compute A1 homotopy invariance. Okay, let me stop here. Thanks so much.
Thank you. Questions? Any questions? Yeah, I have a question. What about if it's non-trivial evaluation?
So over non-trivial variation, there is no, so tropical cohomology is not isomorphic to Zariski-Schiff cohomology. This is because, so in our case, so HPQ trop is 0 for Q is greater than P. And this is not true over non-trivial variation field. Over, so in order to calculate over non-trivial variation field, we need to, so locally, so topicalization over non-trivial variation field looks like topicalization over trivially valued field. So we need to take into account the global difficulty of topicalizations. I'm not sure how to compute it. Okay. Okay.
Other questions? All right. If not, let's thank Ryota for the very nice talk. And so we will proceed tomorrow at 9 a.m. New York time. Thank you.
Thank you so much.